Imagine in a game your player's inventory shows 3 swords, 2 bows and a banana. But you have no idea how they got there. In particular, where did the banana come from? The problem is, if you just maintain state, you lose the history. And this is where the event sourcing pattern comes in. So today I'll show you the basic pattern, plus a few more advanced techniques, such as caching and projections. This video is sponsored by Flocks. I'll talk more about them later. Now, what is event sourcing? Most applications store the result of a series of changes, like a balance, a list of items, a status flag. In event sourcing, you actually never store the final state. You store each change that leads to it. And these changes are called events. For example, item added or item removed. Then if you want to know what the current state is, you replay those events and you construct the state on the fly. Now, this can be useful in, for example, banking, where you want to keep track of transactions and not the balance. Blockchain is also an example of event sourcing, and this has many applications like meme coins and rug pulls. Another example is the tool that 99% of developers use daily, which is Git. I mean, it's not exactly event sourcing, but the core idea is the same. You store every change, never throw anything away, and you derive the current state from the history of changes. Let's quickly build a basic example of event sourcing, and we're going to start with an inventory in a game, the example I mentioned at the start of the video. So we start with nothing more than this empty main file that I have here. So let's add some files. So the first thing that I'm going to do is I will add an event file. And this is where we're going to define the event types that our system is going to work with. So what we'll need is 2 classes. One is going to be an enum with different types of events, and one is going to be the actual event class. So from enum, I'm going to import the string enum type. And then we're going to define an event type class. So let's say we have item added, and we have item removed. Obviously, later on, we can add more types of events here. Then I want to create an event class. So let's use data class for that. And since events are typically write once, we don't want to modify events after the fact, I'm going to make this frozen. This is going to have type, which is the enum that I defined before. And let's say it just has some string data for the moment. And also, it's going to be helpful to have a timestamp so we know when the event was raised. And in order to store that, I'm going to import the date time object. Timestamp is a date time object, and we're going to use the field from data classes to give that a default value. So we're going to use datetime.now as a factory in order to generate this timestamp when we create the event, like so. So this gives us a basic event and event type setup. Next, we're going to need some sort of store that keeps track of the events that have been raised in the system. And this event store is obviously going to need the event. And let's make that a class. So we have an event store, there's an initializer, and the only thing that this is going to have is a list of events. That initially is going to be empty. And then we need some helpful methods, like being able to append an event. Note that here I'm only talking about events. I'm not talking about inventory yet. That comes later. This is not going to return anything. And the only thing that this does is call the append method on the events list. Like so. And then let's also add a method that gets all the events. So this is going to return a list of events. And I'm doing it like so that you actually get a copy and you're not accidentally changing the list of the events in the event store. So this is really simple event store. In fact, you could even decide to not have this at all because it's literally just a list of events. So the basic ingredients for event sourcing are now here, but let's adapt this a bit to our use case, which was inventory items in a game, right? So let's add another file, inventory. And this is where we're going to model the inventory system on top of our event store. So what we need from events, we're going to need the event, and we will also need the event type. And from the event store, we're going to need the event store class. And now I'm going to create a class, inventory. This has an initializer, and what I'm actually going to do is I'm going to supply this with a store object. So that's the event store. Like so. So now we can use dependency injection to provide an event store to our inventory class, which then uses this store to add and remove inventory items. So let's add a method here, add item. And for now, let's say we represent the item simply by a string. This doesn't return anything. So the only thing that we're doing now, we're not storing somewhere a dictionary of items or something. We're actually adding an event. And then if we want to know what the inventory is later on, we're going to replay those events and construct the inventory from that. So in this case, adding an item basically means that we add an event to our event store. So we call append and we're going to supply it with an event. And the event type is going to be item added. And the data that we supply is the item that we pass as a string. So that adds an item. The next thing that we need to add is a method that provides us the items. And this needs to collect that information from the event store. So what I want this method to return is a list. And a list of tuples, where for each item we have the count of that particular item in our inventory. So you get like 2 swords, 1 bow, 3 bananas, etc. And in order to make that a bit easier, I'm going to use the counter class from the collections library. So this will help me quickly keep count of the various items that I'm retrieving from the event store. So the count, that's going to be a counter of strings, because I want to do this for every string item. And for now, initially, that's of course empty. And then I'm going to iterate all over the events. And I'm using the getAllEvents method to do that. And what I'll do is if the event.type equals item added, then counts for that particular item, which is in the data attribute of the event, we're going to add 1. And because I'm using counter here, I don't have to initialize this entry in the dictionary. That's what the counter already solves for me. So that is what actually makes it easier. If an item is removed, we subtract 1 from that particular count. And now what we're going to do is we're going to return a comprehension, and I'm going to get the item and the count. But only if the count is larger than 0. We don't want negative things in our inventory, obviously. So that is get items. So now we have inventory, which is a very basic layer on top of our event store. So let's build a simple example just to see how this works. So from the event store, I'm going to import the event store class. And from inventory, I'm going to import the inventory class. And then in the main function, I'm going to create the store. I'm going to create the inventory. No, not with a capital letter. We're not in Swift or C# land, and I'm going to pass the store like so as an argument. So now I have my inventory, and what I can do then is add a bunch of items. And then let's print inventory.getItems like so. Let's run this and see what we got. So now we have a sword, a potion, a bow, a shield, and a torch. No bananas. We can slightly extend the inventory with a few more helpful methods. For example, let's add a getCount method that for a particular item counts how many there are in the inventory. So this is going to return an int. And what we can do is basically rely on getItems. So I'm going to turn the result of getItems into a dictionary, and that will allow me to get the result of the particular item that I'm passing. And by default, I'm going to return the value 0 if that item is not there. So there we have a helper. And then what we can do in the main function is, for example, print inventory getCount for a shield, like so. Let's run this again. Now you see we get 1 shield. And if we try to find all the bananas, then we will see that there is no banana. Still no banana. I'm kind of disappointed. Anyway, that's one thing we can do to make this a bit easier. And now what we can also do is, for example, have a remove item. And here what we'll basically do is append an event of event type item removed, like so. And of course that doesn't work that way. It needs to be parentheses. Okay, there we go. We can make this a bit more robust, for example, by checking that there is actually such an item. Like so. And now what we can do in the main function is also remove an item. So let's say I remove the shield, like so. Then let's run this again. And now you see that shield is no longer in the inventory when I retrieve that. So this is the basic idea of event sourcing. You don't keep track of the state, you keep track of the changes, and then you compute the state from the changes. Now, at this point, I didn't use a database or something. It's just a list of events. But of course, you can extend this so that these events are actually stored in a database. Now, one issue with this approach is that every time we get the items in the inventory, it needs to compute all of that on the fly. And if you have many, many different events, that's going to take a long time. So typically what you also often see added to event sourcing systems is caching. And this is actually really easy to add in Python. So what I'm going to do is from functools, I'm going to import cache. And what we can do then is take our getItems method and we're going to add the cache decorator. So this will cache the computation of getItems whenever we call that. Now, the only thing we need to do now is make sure that if you add or remove an item, that we invalidate this cache. Otherwise, getItems is not going to give the correct result. Fortunately, this is also really easy to add. So let's say we have a method invalidate cache. I'm putting an underscore here because this is typically something that is only used internally. And what this is going to do from getItem is to call cache clear, which is a method that's added by the cache decorator. And of course, the result here is going to be none, like so. And now we can very easily go into add item and call invalidate cache, if I'm able to type correctly, like so. And this same line, we can add it to removing an item. So let's go back into our main file. Let's run this one more time to see that we indeed get the same result. And then let's say we are going to remove another item here. And we will remove the bow. And let's also finally add that banana. Why not? And now we're going to print inventory.get items. And there we have it. No more bow, but with a banana. And by the way, if you paid attention, all these other methods, like get count, for example, it relies on get item. So that's automatically cached as well, which is really neat. And finally, a note, doing caching like this is actually a lightweight form of projection. We have a derived view that is stored somewhere in memory. Now, before I'm going to continue improving this inventory model, let's take a moment to talk about something that affects every project, which is managing development environments. Now, so far, we've been working in a pretty clean Python setup, but real projects are rarely that simple. You often need more than just Python, maybe some Node scripts, a Redis server, a C compiler for that one weird package that you're using. And of course, it all works perfectly on your machine. That's where Flux comes in. Flux lets you create reproducible, shareable development environments, not just for Python, but for your entire stack. It's like Poetry or UV, but for everything. And it's built on top of Nix. Let me show you how easy it is to get started. Let's say we have a little Python script that simulates 1,000,000 dice rolls using NumPy. This is what the code looks like. There is some missing type annotations and so on. It's not really important what the example is exactly. Then let's initialize the environment with Flux. And now let's activate the environment. And I get an Oh My Z shell update for free. And let's run the file. There we go. That's a clean Python environment with NumPy installed. Now, if you have an existing project already, you don't have to do it this way. Flux can automatically set up the Python environment for you from a requirements.txt or a PyProject YAML file. If you want Redis too, yep, that runs right inside the environment. No brew install on macOS, no sudo or other types of system pollution. It's really neat. And you can also manage services with Flux services, starting, stopping them, and printing the status. You can commit your environment, which is the .flux folder in your directory, to a repository and then share it with your teammates. Or you can push it to Flux Hub. Your teammates clone the repo, activate the environment, and they're ready to go. Python, Node, Redis, CUDA, whatever you need. It works on macOS, Linux, Windows subsystem for Linux too, and gives you the same results across dev, CI, and production. I highly recommend you try them out. It's free at flux.dev. The link is also in the video description. Now, as next step, let's make the inventory a bit more sophisticated. And we'll start tracking not just the item name, but also where it came from, how rare it is. And to do that, we're going to switch to using a proper item data class. And here's what that roughly looks like. So I have a data class item, which has a name, a rarity, and an origin. So now instead of just passing a sort, we can also track where it came from and how rare it is. In order to support items, we need to make the event class more generic. Now we could change the string data that we have here to have an item object, but we can also choose to make event generic. So in this case, we're going to have an event that will have a type T, and T is the type of the data. And default, we can make that a string. So this is using Python's generic mechanism. And this needs to be supported throughout the chain. So we have the event here, but the event store now also needs to be generic, like so. And then the events is going to be a list of events. And each of these expects an event of type T, like so. So now in the future, if we want to use this event store for other types of things, we can actually do that. Now there's still the issue of the event type being a string enum. You could opt to turn this actually into a string. So then you can have any different type of event that you want. And you're not dependent on this string enum. But I'll leave it like this for the time being. And then of course we also need to change things in the inventory, because now the event store is generic. So what I'll do here is from item, I'm going to import the item class, and I want an event store of type item, like so. And then we'll need to change a few more things here as well. So for example, add item expects an item, and remove item also expects an item, like so. And then the only thing we need to fix is the count, because this is a string value, so that simply doesn't work. So what we need to do then is collect the name of each item, like so. And then we're going to add that as an index to my counter. And then finally, of course, we also need to update the main file. So I already prepared this. So what I'm doing here is I'm creating a bunch of different items, some swords, potions, bows, whatever. I set up a store and an inventory just like before. I add a couple of items, remove a couple of items, and then showing the inventory and also counting the number of swords in the inventory. So let's run this. And now I get some problem. And the issue is that in inventory, I forgot to change something. So get count actually also needs to pass an item type. And then here we need to search by item.name, like so. Let's try this again. That doesn't work either. The reason it doesn't work is because in inventory, I forgot to add .name to this check, like so. Let's run this again. And now it works. Final thing that I want to quickly show you is that because now we have a full history of what happens, we can actually build projections on top of this system. So here I have a couple of examples. So for example, here's a projection called get most collected items. And this returns a list of the most frequently added item names. So basically that's going to look at the events and then count the number of occurrences and then simply return the most common ones. Or here's another projection, which is get item origins, that returns a mapping of item names to all the origins that they've appeared in. So there for each added item, I'm adding the origin to it for that particular inventory item and then return that as a dictionary. And then I can simply extend the main file by calling those projection functions on the event store that we have until now. So let's run this one more time. And then you see we still have the current inventory, but now we also have the most collected items and the item origins. And note that these functions don't change the state in any way, they just analyze it. And of course you can build more projections on top of this. Items by rarity, time-based graphs, even per player breakdowns. And by the way, if you want to learn how to design software like this from scratch, I have a free guide for you. You can get this at ArjanCodes/design guide. This contains the 7 steps that I take whenever I design new software and help you avoid some common design pitfalls. The link is in the video description. Now, event sourcing. There's lots of pros to this. You have the full history. You can audit it, debug, or time travel. The state is rebuildable, so you can replay this from scratch or build new projections at any time you want. Also, the logic is decoupled, so the write and read models, they are basically separate. And there's powerful analytics. If you have projections, you can build those and it gives you a lot of insight without actually cluttering the core logic. You have immutable data. Each event is basically a fact that you don't overwrite in the future. But at the same time, there is also cons to event sourcing. So obviously it's going to be more complex than just keeping track of the state. The queries might be harder. You can't just select everything from the inventory. You need to replay that first or project it. Event schemas might evolve. So if you change the event format later, then old events will need migration. And of course, it's not always necessary. You know, if you don't really care about history in a particular setup, then this is overkill. So use it when you need traceability, rollback, or auditing. If your domain is complex or highly dynamic, if you want to derive multiple views from that same data with CQRS, for example, a pattern I will discuss in a separate video. Or maybe you need time-based analytics or debugging, then this is very helpful. But don't use it if you're just building something really small or temporary and you just need a simple CRUD operation. Also, if you have very strict performance needs, this might not be the optimal pattern for you. In summary, as you've seen today, event sourcing is a pattern where you store the changes and then build the state from that. So I started with a simple example with just strings and then adding caching, evolving to a complete item data structure and build custom projections all from that single stream of events. Now, I'd love to hear what you think. Have you used event sourcing before? Are there current projects that you're working on where you think, oh, that could actually work pretty well here? Let me know in the comments. Also, if you have other specific patterns in mind that you'd like me to cover in a video, let me know in the comments. Now, if you enjoyed this video, check out this playlist for more in-depth design pattern discussions in Python. Thanks for watching and see you next time.